This is part 2 of lecture 4.4, one-to-one and onto functions. In this video, we will define an onto function, learn how to prove if a given function is or is not onto a particular set, and relate the property of being onto a set to the composition of two functions. Given a function f from a set A to a set B, f is said to be onto B, or surjective, or a surjection, if and only if, for any element y in the set B, there exists an element x in the set A such that y equals f of x. It follows that f is onto B if and only if, for any element y in the codomain B, y has at least one pre-image. That is, if and only if the range of f is equal to B. We will sometimes use the following notation to denote that f is a function from A to B that is onto B. Here are some Venn diagrams illustrating some surjective functions. For a function to be onto the set B, the only requirement is that the range is equal to the set B. This is clearly satisfied by the two functions shown here. Note that it is not necessary for the function to be one-to-one. Hence, the function at the bottom, in which there are two elements in the domain that share an image, is also onto B. The two functions on the right are not onto B because in each of them, there is an element in B which has no pre-image. For any non-empty set A, the identity relation I subscript A is a surjection from A to A. This follows from the fact that for any object y in A, y is equal to I sub A of y. So any y in A is its own pre-image. Also, the empty relation is a surjection from the empty set to the empty set. Indeed, observe that the empty set is equal to the Cartesian product of the empty set by the empty set. Let F denote the empty relation. The statement for any object y in the empty set, there exists an object x in the empty set such that f of x equals y, is equivalent to the statement for any object y, if y is in the empty set, then there exists an object x in the empty set such that f of x equals y. The statement y is an element of the empty set is clearly false. So the condition if y is in the empty set, then there exists an object x in the empty set such that f of x equals y is true. This holds for any object y. Hence, the entire quantified statement is true, and the empty set is indeed a surjection from the empty set to itself. Consider the function f consisting of all ordered pairs xy of real numbers, satisfying the equation x plus y equals x times y. We claim that f is a surjective function from the set of all real numbers not equal to 1 to the set of all real numbers not equal to 1. That is, for any real number y not equal to 1, there exists an x such that x is a real number not equal to 1 and y is equal to f of x. We have proved in an earlier example that f is a function from the set of all real numbers not equal to 1 to the set of all real numbers not equal to 1. It remains to show that f is surjective. To do this, let y be an arbitrary real number not equal to 1. Take x to be the quotient y over y minus 1. Since y is not equal to 1, the denominator y minus 1 is non-zero. Thus, x is a real number. If x equals 1, then y must be equal to y minus 1, which gives us 0 equals negative 1, which is false. Hence, we have a contradiction. So x is not equal to 1. Hence, x is a real number not equal to 1. Moreover, x plus y is equal to y over y minus 1 plus y. It can be shown that this is equal to x times y. We leave the details as an exercise. Therefore, the ordered pair xy is an element of f, and thus y is equal to f of x. So f is onto the set of real numbers not equal to 1, as claimed. Consider the function g consisting of all ordered pairs xy of real numbers, satisfying the equation y equals x squared. We claim that g is not onto the set of real numbers. That is, it is not the case that for every real number y, there is a real number x such that y equals g of x. Equivalently, there is a real number y such that there is no real number x for which y equals g of x. Indeed, consider negative 1. Negative 1 is a real number, but no real number has square equal to negative 1. So g is not onto the set of real numbers as claimed. Let us now look at how the property of being surjective affects the composition of functions. Given functions f from a to b and g from b to c. If f is onto b and g is onto c, then the composite function gf is onto c. If the composite function gf is onto c, then g is onto c. We first prove statement 1. Assume that f is onto b and that g is onto c. We are to show that the composite function gf is onto c. That is, for any element small c in the set capital C, there exists an element small a in capital A such that C is equal to gf of A. To show that, let small c be an arbitrary element of capital C. We need to show that some element small a in capital A has image small c under the composite function gf. Since the function g is onto c, small c is the image of some element small b in capital B. Since the function f is onto c, or rather onto b, small b is the image of some element small a in capital A. So small c is equal to g of small b, which is equal to g of f of A, which is equal to gf of A. Therefore, the composite function gf is onto c, which proves statement 1. Next, we prove statement 2. Assume that the composite function gf is onto c. We need to show that g is onto c. That is, for any element small c in capital C, there is an element small b in capital B such that g of small b is equal to small c. To do this, let small c be an arbitrary element in capital C. We will show that c is the image under g of some element small b in capital B. Since GF is onto C, small c is equal to GF of small a for some element small a in capital A. Hence, small c is equal to G of F of small a. Now, f of a is in the set capital B since f is a function from A to B. Thus, C is equal to G of B for some element small b of capital B. Therefore, G is onto C, which proves statement 2. It is not true in general that if the composition GF is onto C, then the function f is onto B. To show this, we need to give specific functions f and g such that the composition GF is onto C but f is not onto B. Consider the functions f and g, where f is the natural exponential function from the set of real numbers to the set of non-zero real numbers, and g is the function from the set of non-zero real numbers to the set of real numbers, with g of x equal to the natural logarithm of the absolute value of x for each non-zero real number x. Then the composite function GF is a function from the set of real numbers to the set of real numbers, with GF of x equal to the natural logarithm of the absolute value of the natural exponent of x, which is equal to the natural logarithm of the natural exponent of x, which is equal to x for every real number x. Hence, the range of GF is the set of all real numbers. So GF is onto the set of real numbers. However, the function f is not onto the set of non-zero real numbers, since, for instance, there is no real number whose natural exponent is -1. Therefore, the functions f and g are the desired counterexample. You have come to the end of part 2 of lecture 4.4. You may now proceed to part 3. Thank you for your attention.